Hi, I'm Paul Kyogan from GK Tuition, and in this video I want to talk to you about area, volume and measurement. Now the question that I've chosen to go through here is 2017 Paper 2 Question 7. In the first part of this question we're given two different diagrams. Figure 2 is just a sphere that has a radius of r. Figure 1 is a cylinder that has a radius of r and a height of 2r. And inside the cylinder, two cones of radius r and height r are placed so that they're touching at their vertices. In the first part of this question, we need to find the volume or the capacity of the cylinder. So that is the empty space, that when the two cones are in the cylinder, what is the volume of the rest of the space? So you need to realize that in order to work out the capacity of figure 1, or in other words the volume of figure 1, it's the volume of the cylinder minus the volume of the two cones. It's relatively straightforward to get the volume of a cylinder, it's just pi r squared h. It's relatively straightforward to get the volume of two cones, it's 1/3 pi r squared h multiplied by 2. I've already written out my dimensions here, so all we need to do is sub in. To get the volume of the cylinder, it's just pi times r squared times 2r. And if I simplify that down, I just end up with 2 pi, and then r squared by r is r cubed. So the volume of the entire cylinder is 2 pi r cubed. But now I need to subtract the volume of the two cones. So in order to get the volume of one of these cones, it's 1/3 times pi. The radius is just r and the height is just r. Which means if you simplify that fully, you would just get 1/3 pi r cubed. So obviously I want to get two of those, so it's going to be 2 times that. If I multiply that by 2, the volume of the two cones is just 2/3 pi r cubed. So if the volume of the original cylinder is 2 pi r cubed, and the volume of two of the cones is 2/3 pi r cubed, I need to subtract the cones from the cylinder to work out the capacity of the empty space in figure 1. Notice that these are like terms, they're both pi r cubes. So 2 minus 2/3 is just 4/3 pi r cubed. Now be very careful, in this topic it's so important that you always put in your units. So in this case, because my radius and my height are in centimeters, that means that my volume is in centimeters cubed. Where the capacity or the volume of the empty space in figure 1 is 4/3 pi r cubed. Now I need to prove that this is the same as the capacity or the volume of the sphere. So to conclude this one, it's relatively straightforward. The question was to prove the capacity of figure 1 is equal to the capacity of figure 2. Well, the capacity of figure 1 is just the volume of empty space in the cylinder, which we've already worked out is 4/3 pi r cubed. The capacity of figure 2 is just the volume of a sphere, which we can read straight from our log tables. The formula for the volume of a sphere is 4/3 pi r cubed. And if the radius of this sphere is r, then to work out the radius of the sphere in figure 2, we would just sub in r instead of r, and it's actually just the same as what's in the log tables. So I know that 4/3 pi r cubed is clearly equal to 4/3 pi r cubed, so I could just take it and I verified what they asked me to verify. In B part 1, we're told that the radius from here on out is 12 centimeters. That water is poured into the sphere and into the cylinder up to a depth of 6 centimeters. Figure 4 represents what is happening at the sphere. What I have at the bottom here is water to a depth of 6 centimeters. And I now know that the radius, the distance from the center to B, is 12 centimeters. The question asks me to use this information to find AB in surd form. Now, what you need to recognize is that clearly the radius is from here to B, but also the radius is also from the center going directly down. And I know that the distance, the depth of water, or in other words, the distance from here to here is 6. So by extension, the distance from A to the center must also be 6. Now you have a right angle triangle and you know two sides, so to find the third side I just need to use Pythagoras' theorem. If I sub in here, I could say that AB squared plus 6 squared is equal to 12 squared. If you simplify this down, you end up with AB is equal to 6√3 centimeters. In B part 2 here, we're asked to find the distance CD. Now in order to find the distance CD, you should realize that you're using similar triangles. So I've drawn this triangle, I've taken it from figure 3. We had the distance CD in figure 3, and I've just labelled these points as X, Y, and Z. So if you think about it there, my X is the center, is the top of the bottom cone, and it's also, say, the center of the cylinder. Y is at the base of the cylinder, and Z is at the edge of the cylinder. So I've just labeled in X, Y, and Z to make it easier. We know that the radius of the cylinder is 12. So obviously I know the distance from Y to Z is just 12. And we know that the height of the cone is 12 as well. So it's the distance from X to Y, and the height of the cone is just 12 centimeters. And in the previous part of the question, they told me that the distance from C to the bottom is 6 centimeters. So that's the information that we already have. Obviously, if I know that this whole distance is 12 and that this distance is 6, I just subtract them to find that the distance XC is 6 as well. So the distance from the top of the cone to the point C is 6 centimeters. Now, you should recognize that the triangle XCD and the triangle XYZ are similar. You don't have to prove they're similar. In this case, we can just assume that they're similar. That angle and that angle are corresponding. They're both right angles, and that's a common angle. Remember, when you know that you have similar triangles, that means their sides are proportional to each other. So straight away, once you identify their similar triangles, you could write out this. XC, the side of the smaller triangle, divided by XY, the side of the bigger triangle, will be equal to CD, the base of the small triangle, divided by YZ, the base of the big triangle. Now luckily for us, if we sub into these two fractions, the only thing we don't know is CD. So it's relatively straightforward from here. XC is 6, XY is 12, CD is my unknown, so we can leave it as CD, and YZ in this case is 12. Now you could cross multiply and solve this one, but clearly since they're both over 12, then the top of this fraction is equal to the top of that fraction. So straight away we can just say that the distance CD is equal to 6 centimeters. In B part 3, I'm asked to verify that the surface area of the water in the cylinder is equal to the surface area of the water in the sphere. Now let's look at figure 3 first, because figure 3 is going to be the harder one to figure out. Imagine that so there's water up to a depth of 6 centimeters. Imagine if we just chopped off all the rest of that diagram. I'm only concerned with the first 6 centimeters of that diagram. Imagine then if you chop that off and it was only 6 centimeters tall. Imagine then if you just looked straight down into it. If you looked straight down into that, it would look something like this. So the outer rim is clearly just the outer rim of the cylinder. And I know that the radius of the cylinder is 12. Okay, but my squiggly lines here represent the water. They're all around the outside. But in the middle of that, there's a cone, and there's obviously no water in the cone. So there's also the shape of the cone. If I cut it off at 6 centimeters, it would be a circle. So there's a circle on the outside, and the outside of this, and this bit here is filled with water. But there's a circle on the inside as well where there's no water. Now in B part 2, we worked out that the radius of this was 6 centimeters. Or in other words, the distance from C to D was 6 centimeters. Using that, we can now get the surface area of the large cylinder and subtract the surface area of the cone in the middle. And then if I do that, I'll be left with just the surface area of water, which is along the outside. Now the radius of the cylinder, or this outer circle, is 12. To get the area of a circle, it's pi r squared. So in this case, it'd be pi by 12 squared, which is 144 pi. We've worked out the distance from C to D is 6 centimeters. By extension, the radius of this circle in the middle is 6, which means if I'm getting the area here, it will be just pi by 6 squared, so that works out as 36 pi. The whole thing is 144 pi. The bit in the middle where there's no water is 36 pi, which means that the total surface area of water in figure 3 is 108 pi centimeters squared. Now, to work it out for figure 4, it's relatively straightforward. Because obviously, imagine if you look at figure 4, clearly the surface area of water in that sphere would just be a circle. It's just a plain circle. The area of a circle, as I said there, up here, the area of a circle is just pi r squared. And in B part 1, we worked out the radius of that water. The radius of that water is 6 root 3, which means if I was to get the area of this, it would just be pi by 6 root 3 to be squared. So the surface area of water in the sphere is equal to 108 pi centimeters squared. Now to finish it off, you could say that the surface area in figure 3 is equal to the surface area in figure 4, so therefore you've verified what they asked you to prove. In the last part of this question, we're told that the volume of water in the available space in the cylinder is equal to the volume of water in the available space in the sphere. Okay? And then we're asked to find the volume of water in the sphere when the water is at a depth of 6 centimeters. So obviously we can't actually work it out in terms of the sphere, but we can work it out in terms of the cylinder. Whatever the volume of water is in the cylinder up to 6 centimeters, that is the same as the volume of water that's in the sphere up to 6 centimeters. So you'll notice that I've drawn a diagram here. I'm only concerned with the bottom half of the cylinder. So I'm only going to use the bottom half, and this diagram represents the bottom half of the cylinder. In order to figure this out, we're going to have to use we're going to have to get the volume of a few different things. The first thing that I want to do is get the volume of a cylinder that has a radius of 6 centimeters. In other words, find the volume from this point just halfway up, even if that frustrum in the middle wasn't there. So I'm just going to get the volume of a cylinder, and the formula for that, the volume of a cylinder is pi r squared h. Now clearly the radius of this cylinder is 12 centimeters, and the height of the cylinder, I'm only concerned with the first 6 centimeters. So my height in this case is going to be 6, my radius in this case is going to be 12. So if I sub that in, the volume of that cylinder is pi times 12 squared times 6. And if you plug all that into your calculator, we can leave it in terms of pi, but it works out as 864 pi centimeters cubed. So the volume of a cylinder that has a height of 6 centimeters is 864 pi centimeters cubed. Now, obviously what I want to do is I want to find just the shaded bit, the bit that I've shaded there, or in other words, just the water that's around the cone. So the first thing I'm going to have to do is I need to work out what is the area of this shape here. This is referred to as a frustrum. Basically, if you have a cone and you cut off the top of it, the bit that's left at the bottom is called a frustrum. Now, the easiest way to do this, what we're going to do next is we're going to find the volume of the whole cone at the bottom. Then we're going to find the volume of the smaller cone that's at the top and subtract the two. If I do that, that will tell me the volume of the frustrum, or in other words, the volume of the cone up to 6 centimeters. If I can get the volume of this frustrum, subtract it from 864 pi, that will tell me the volume of the water. So let's just break it down here. The first thing I'm going to do is get the volume of the big cone. In other words, the cone that has a height of 12 and a radius of 12. The volume of a cone in the log tables is 1/3 pi r squared h. In this case, the radius of my cone is 12 and the height of my cone is 12. Which means that the volume in this case is 1/3 pi, my radius is 12 squared, and my height is 12. If you plug that into your calculator, the volume of that cone is 576 pi centimeters cubed. Okay, so that's the volume of my large cone. Now I want to find the volume of the smaller cone. Basically, I want to find the volume of the cone if I cut it off at that point. What is the volume of this smaller cone? Remember, the height of this cone is 6, and in the previous part of the question, we've worked out that the radius, or the distance CD, is 6 as well. So you know the radius of this smaller cone is also 6, which makes it relatively straightforward for us now to find the volume of the smaller cone. We're subbing into the same formula, 1/3 pi r squared h. And so I'm subbing into 1/3 pi r squared h, and luckily for us in this case, we know that the radius is 6, so it becomes 6 squared, and the height is 6. So I just multiply it by 6. Now you plug all that into your calculator, it works out as 72 pi centimeters cubed. So let's consider these two bits. I know that the volume of the cone, the large cone there, is 576 pi centimeters cubed. The volume of the small bit that's at the top is 72 pi centimeters cubed. The reason I got the 72 pi is because if I'm only looking for the height of water up to 6 centimeters, this part of the cone is irrelevant. So what I want to do now is subtract those two values. The volume of the big cone is 576 pi. The volume of the small cone is 72 pi. If I subtract those two, I get 504 pi centimeters cubed. That figure refers to the volume of the frustrum, or in other words, it refers to the volume of cone up to 6 centimeters. The frustrum is if you just cut off the top of the cone and you're just left with this bit. The very first thing I did in this question was I found the volume of a cylinder that has a height of 6 centimeters. And that works out as 864 pi centimeters cubed. If I now subtract the cone in the middle, all I'm left with is the remaining area, or in other words, the remaining available space that the water would have filled. So 864 pi minus 504 pi, my final answer there works out as 360 pi centimeters cubed. So the available space in the cylinder is 360 pi centimeters cubed. Obviously, that is the volume of water. If you poured water into it up to a height of 6 centimeters, that's the volume of water in the cylinder. And they told me in the question the volume of water in the cylinder is the same as the volume of the water in the sphere. So in fact, we've worked out the volume of water in a sphere up to 6 centimeters. So I hope that makes sense now. If there's anything you're unsure of there, just make sure you let me know. Let me know in class, or send me an email, or get in contact with me some way. I'll try and clarify it, or I'll try and explain it differently for you.